We discussed in an earlier lesson how two harmonic waves meeting at a point can either constructively or destructively interfere, producing either a bigger wave or no wave at all, depending on the phase difference between the two waves when they meet. The interference of sound waves presents very interesting phenomenon, and we will spend few minutes looking at some of these phenomena. Interference of sound waves. Sound waves advancing in the same medium will generate two separate displacements on the same set of particles. For example, this is an air molecule. If there are two loudspeakers in this room, sound coming from both loudspeakers will interfere. In other words, the energy coming from both loudspeakers will produce displacements on this particle. If both displacements are in phase, the particle will have maximum displacement. In other words, you will hear a loud sound. If the two waves are out of phase, the particle will not vibrate. In other words, the sound will cancel each other. You will hear no sound. Now, this is a very interesting phenomenon. If two waves are in phase, these displacements will add up, producing a larger displacement. And in the case of sound, that means a loud sound. Now tell me, what does loudness of a sound depend on? Loudness of a sound depends on the amplitude of vibration. Now, for example, here I have a tuning fork. If I hit it very lightly, now I'm going to hit it very lightly, the energy I imparted to it is very small, means the amplitude of vibration is very small. But if I hit it a little louder, look at that. You can actually see the vibrations, large amplitude vibrations. So loudness is proportional to actually the square of the amplitude. A larger amplitude means a louder sound. So if the two waves interfere in phase, these displacements will add, producing a larger displacement, which means a louder sound. So here we have the case of two sound waves meeting in phase at a point. The compression, remember I told you, I will use the transverse wave representation to represent a sound wave, a longitudinal wave, where the crest represents a compression and the trough will represent a rarefaction. So the compression of one wave falling on the compression of another wave will produce a bigger compression. There you have a bigger amplitude and therefore a loud sound. Since the loudness of a sound is proportional to the square of the amplitude, you will hear a loud sound. If two displacements, on the other hand, are out of phase, the displacements they produce on the particle of the medium will cancel each other, and the resultant displacement will be either zero or very small, depending on the phase difference. Now, here you have the compression of one wave falling on the rarefaction of another wave. The waves are completely out of phase. The displacements are cancelled. There are no displacements. You will hear no sound. The loudness will be... Now here I have an animation. It may be difficult to figure out, but what happens is a sound advancing from the left and a sound advancing from the right superimpose one on each other. That means each particle will now be subjected to compressions and rarefactions from both waves. When compression falls on compression, you can see a region where you have a thicker shading. It shows a compression falling on a compression, producing a bigger compression, and rarefaction falling on a rarefaction, producing a bigger rarefaction. So a good example of how two sound waves interfere, producing either a loud sound or a low sound. Now, once again, the compression falling on a compression produces a large compression. A rarefaction falling on a rarefaction produces a large rarefaction. And this is what we call constructive interference. The compression of one wave falling on the rarefaction of another wave is completely destructive, producing no sound. I have another animation here. This is the case where you have two loudspeakers in a room, and if you walk from one end of the room to the other, what you will hear is actually amazing. Now, if you walk from one end to the other, there are regions where sound from each of the loudspeakers will meet in phase, producing a loud sound. And as you move further, there are regions where they will be out of phase, having no sound. So, in a situation like this, if you are very careful and listen very carefully, you can pick out places where the sound is loud and there will be no sound, loud sound, no sound, and so on. Now, in practice, it is actually difficult to get this effect done. You know why? Because when you do this experiment in a room, it is not only the direct sound coming from the loudspeakers that you hear, but also the sound reflected from the walls and the ceiling. So even at places where the two sounds from the loudspeakers cancel, you still hear the reflected sound. Also, another factor which will make it difficult is the frequencies that are produced by the two speakers have a wide range of frequencies. Now, not all frequencies will be meeting in phase and out of phase at the same time. So both these will actually make it difficult. But if you do this in a very insulated room, you can actually get that effect. Once you got two speakers producing sound of the same frequency, and if you walk from one end to the other, you can stop at a point where you hear a loud sound, then you can stop at a point where you hear no sound, and so on. A very interesting experiment. So the illustration on the right shows two speakers producing sounds of the same frequency. You see, the experiment will work only if both speakers produce the same frequency and wavelength. Now, if you walk from A to B across the room, at some points sound waves from S1 and S2 will reach you in phase, where you will hear a loud sound. And along the red lines, I have actually drawn some red lines, but that will keep changing. So you can see sounds from S1 and S2 will meet in phase along those lines. And along the green lines, they are out of phase. So as you walk from A to B, if you cut the green line, that is where you hear no sound. If you cut the red line, that is where you hear the loud sound. So you can actually pick and mark points where the sound is loud, no sound, loud sound, and so on. A very interesting experiment. Now here, this is the sound waves coming from speaker 1. and this is the sound waves coming from speaker 2. You can see here my aluminum pointer. If you can see, the compression of waves from speaker 1 falls on the compression of the waves from speaker 2. What's the result? The result is a big wave or a loud sound. So at points where this happens, you hear a loud sound. On the other hand, if the compression of the waves from speaker 1 falls on the rarefaction of the waves from speaker 2, what will happen? They will cancel each other. There will be no waves. You hear no sound. Alright. Another animation of those. Sound coming from speaker 1 and sound coming from speaker 2. If you look at this particle, look at that. This particle, now they are in phase, maximum displacement. And now they are out of phase, no displacement. You see? You can see these two waves will get in phase, out of phase. Look at that again. Maximum displacement. They are in phase now. Now they are completely out of phase. Now here you have two waves of slightly different frequency. That means they have different wavelength. As they advance from left to right, they get in phase and out of phase continuously. We will talk about this towards the end of the lesson today. Here you have now, look at this particle now. There's maximum displacement, the waves are in phase. And soon they are out of phase. And then they get in phase. And that happens continuously. And what will be the effect that you hear? When the waves are in phase, you are likely to hear a loud sound. So here you have loud sound, and now followed by no sound. Alright, loud sound now, followed by no sound. We will talk about this a little later as we move on. Let's now talk about phase difference.